Java
Thank
Language
you.
Update, presented by Viktor Klang.
All right. So I hope you've all had a good lunch and perhaps some coffee as well. I am here today to talk to you about what's been happening in the Java language recently. And I'm going to channel my inner Brian Gitz. So that's my plan for the day. And it's been a lot of things happening. So if we have a look at it. So in the sort of the past 4-ish years, we've received things like records, sealed classes and interfaces, pattern matching in various increments, a revamp of Switch, text blocks, string templates, they are in preview. And what's interesting as well with preview, when we do features and they go into the preview state, they are what we consider to be production quality. So presuming that nothing else happens and new information comes to light, which would have us make any changes that we wouldn't be able to do otherwise, we consider them to be production quality. So preview is a way for you to provide us with information that we might not have known before. So be sure to provide feedback on our preview features. It's super helpful, and while we try to think of everything, sometimes you might miss some combinatorial explosion of things, so it's always good to have a point where you can make that change that you cannot do afterwards, when the thing goes in as a finalized feature. With that said, unnamed patterns and variables, also in preview, unnamed classes and instance main methods, also in preview, and statements before super. And while each of those features are standalone in a sense, what we try to do is when we create features for the language, we want them to play along with other features so that things can be composed well. So can I have a quick just show of hands? How many of you are on Java 8 or before? Just a quick show of hands. Java 8 or before? All right. Up to Java 11? Cool. 17? Whoa. 21? Early access? All right. Cool. So let me give you a brief recap, or brief, right? I have 50-ish minutes, but I'll do my best here. So, records. I don't know about you, but I'm pretty excited about records, and I use records a lot myself. And a record class models a nominal tuple, so something which has a name. And that is important, because in Java, most things have names, and we're used to using names because they convey meaning. And a record wants to be an immutable representation of some state description. And what we can do with that description is to derive APIs for it, like a default two-string implementations or equals or hash code. But you can also have it implement interfaces, and you can add other methods as well. And some methods that are generated you could also override. So they behave very much like things that we expect from using classes and interfaces before. So if you look at the definition of record up there, the point with the x and y ints, it's sort of clear if you know that this gives you a equals method, it gives you a two-string method, and it gives you functionality that I will explain later as well. It's pretty terse, right? It's short, concise. And that's nice, but that's not really the point. Because what we get from the semantics of record is more important than that. So look at it as a bonus that it also allows to have more concise code. It also has an implication. Having this state description for records and having a set semantics for records also allow us to special treat records when we serialize. So instead of having to instantiate an object without calling a constructor and then writing fields to it, we can read the components and then invoke the canonical constructor in the record, passing those components in to form the new record. So that means that you will get the constructor validation applied when you deserialize it. A very useful feature. But you say, what about everybody? I actually, yesterday evening, I had a conversation, or yesterday afternoon, about tuples. And tuples, just anonymous pairs, they can be great in languages that have structural type systems. But Java's type system is primarily nominal, names, right? Because to us, names matter. When you look at code and you only see the structure, it can be hard to review that code in a pull request, or even going back to your old code that you wrote half a year before, and you have like int to bool int string. It's hard to reason about when you just look at it like that to know what it does. So by having names, it's easier to infer intent and meaning. It's sort of the same story as we did when we did lambdas. So instead of having anonymous functions and anonymous types of functions, we gave them names. We have function and bifunction and consumer and supplier, etc. And it's important also to recognize that the record feature is not about generating things, generating syntax, or generating source code. It's about having the semantics associated with having the feature, the knowledge what that feature provides. So a record is the full description of that data. And there's a strong contract such that if you take the values out of the record and provide them as parameters to the constructor, you create something that is equivalent. It's an important thing. It can provide things like being able to do deconstruction and reconstruction. Makes sense, I hope. If at any point you have a really important question, don't hesitate to, and I'll try to locate you in the room. I have some strong lights in my eyes, but I'll do my best. All right. The next feature, sealed classes and interfaces. So what is that all about? Well, if you think about it, being able to specify that an interface or an abstract class or even a class can only be extended in a certain context, a bounded context, and being able to specify which is allowed implementations are, generalizes the concept of class finality. So if you have a final class, what you're saying is, this class will not have any subclasses. That is important information. It allows you to reason about, will there ever be something that extends this and overrides that method? But this feature, the sealed classes and interfaces feature, allows you to be more granular about that, and allows you to be more flexible about that. An important point here is if you omit the permits clause, it infers that to be the all subtypes extending or implementing this within the current compilation unit. So what is the point? Why do we want to be able to directly model A is either A or X is either A or B, and nothing else, ever? Well, it should be able to give us more information to use when we compile the code, right? So if the compiler knows that there will not be any other instances of this type than A or B, then we can use that information. But it also allows library developers, if they expose an interface or a class as a return type, to control whether someone else can actually extend or implement those classes or interfaces. And that is important because when it comes to maintainability, if you don't know what someone else is going to do with your thing, then it's also really hard to design that thing. So by being able to limit how others can extend or implement your own types, that also gives you more freedom on how you decide to implement it. So if we take these two features together, records and sealed classes and interfaces, we get what's called algebraic data types. And it allows us to combine these two features to form something which has a known set of implementation and none else. And some languages, this is your primary means of abstracting data. And this is pretty general in and of itself. And I will show you later what this means. But so this is a really simple example here, the code in the box. If you have some expression type, and of the different types of expressions that you can have, those are sums, products, negations, and constants. You now have a language to describe this domain. And the data is on the outside, because they are records. They have their state available to the outside world. So if we combine this later, let me give you another feature, then throw it into the mix. How many of you have used this feature? Being able to do pattern matching? Yeah, that's a good amount of people. Exciting. So I've been writing Java code several decades, and I've run into this a lot of times, where you write code, you do instance of checks, and then you cast the thing that you tested, but it doesn't necessarily need to be the first statement after the branch, right? Something else that could be logging, etc. And the bigger the distance between the test and the cast, the higher the risk of forgetting to change either when you change one, right? So by being able to say that if this thing is a string, then give me something new that is that string. So it tests, casts, and binds the result to a new variable. Super powerful, and gets rid of a class of things, or a class of bugs that can creep up in applications. So, interestingly, it's pretty sophisticated. So, by doing this, we also need to be able to reason about, okay, so it's not only that you do a test in an if, you typically have some logical condition in there, and you want to be able to take the knowledge that you've already proven to be true and use that information at a later step. So being able to say that if it's a string and its length is greater than 0, it would be weird to have to repeat that cast in the second branch, right? So the type information flows with the logical expressions. And if you didn't do this, you couldn't use common refactorings like invert conditional, and it would still work. So if you have the negated version below, then S is only in scope in the else branch. So if you would invert that, it would only be in the first one. And this is one of those features that if you weren't told this, it would just work. And it's just a very natural way of writing the code. And those are simple patterns. We can have some more sophisticated patterns, like record patterns. So what a record pattern allows us to do is to be able to look at not only the type, but also look at the contents within. So let's say that we define a circle to have a point, which is also a record that we saw before, and a radius. We can do a type test and be able to extract the contents of that value of shape there, so that we can get access to the center and the radius immediately within that branch. And it's also possible to not have to repeat the type name in the match as well by having bar there as well. So, looking at the composition of these types of things, if we have defined a point to be an x and a y, an int, and the circle being the center point and the radius, then when we create an instance of this, we do new circle, new point, we provide some x and some y, and then some radius. And that is your construction of this record. But when you want to do the inverse, you want to deconstruct it, you want to look at what is this, and give me the components. If you look at that code over there, they are very, very similar. And that is not by accident, because they are inverses. Being able to put things together and being able to take them apart. And when you do a pattern match, if it's composed or if it's a more simple expression, the entire thing has to succeed or not at all. So when you compose it, it has to succeed at all. You can nest these things as well, right? As we saw before. But sometimes you don't want to have to repeat everything when you don't need everything. So there is a preview feature called unnamed patterns and local variables that allows you to use the underscore to say that there will be a thing here, I don't necessarily care what it is. I'm not going to use that anyway, so I don't want to have to repeat what it is. So it allows you to be more explicit about what information you're actually going to use. So, going back to the let's see what these features together enable us to do is, if we go back to our domain that we defined before with the expressions, and we have sums and products and negations and constants, if we want to define behavior that operates on this structure, we can now define that inside the expression, or we can define that on the outside, because the structure is available to the outside. So you have more choice as to where you want to put logic. So sometimes adding I don't know if you've had this situation occur before, where you have a use case, you have a domain model, you have a use case, it's a specific use case, but the only place where you can actually add the behavior is on the class itself, because it needs to have some internal state to that class. But the use case is a very slim one, but it ends up being exposed to everybody that uses the class. So this approach here would allow you to be more selective as to where you want to expose that new behavior. But more importantly, it also allows you to add behavior after the fact. So let's say that someone else defined this algebraic data structure or data type. You can now add your own functionality on the outside, because you're able to see all the structure and inspect all the structure. So in this case, let's say that if we want to implement an evaluator for set expressions that evaluates to an integer, we can look at the expression to see if it's a sum, then we evaluate the left-hand side and add that to the evaluation of the right-hand side. If it's a product, we do the same thing, but instead of doing addition, we do multiplication. If it's a negation, then we evaluate the expression and then we negate it. And if it's a constant, we return that constant. So that allows us to recursively decompose this algebraic data type into functionality on the outside. So what is the analogy here? Well, if you look at what we've done in Java for a long time, is the visitor pattern. And the visitor pattern sort of forces the thing that supports being visited to implement that logic. Something needs to implement such that it can visit things internally. It needs to ferry the behavior on the inside So taking behavior on the outside and passing it internally. But if we wanted to differentiate an expression instead of evaluating it, and the maths here doesn't matter, it's beyond the point here. The point here is adding new behavior after the fact on the outside is now possible because you have the ability to look at the data, modify the data, construct representations using that data. So why are we doing this? Well, it's about being able to model data as data. So classic object-oriented programming is really good at defining boundaries and modeling complex relationships between entities and processes. And it allows us to do encapsulation, to separate the implementation from the interface. We can do polymorphism. We can also package up such that the state moves with the behavior, so we can pass it around. And it allows it to do a form of modular reasoning, because we know what can access what. What is a boundary and who is on the inside of that boundary and who is on the outside of that boundary. And those can be different kinds of boundaries. It could be different maintenance boundaries for different teams or people working on the code. It could be versioning boundaries. What parts of the code deals with what version of the code? Compilation boundaries, what should be compiled together or shouldn't be compiled together. Security boundaries, such as where is our boundaries of trust within our system? What checks have been passed at which point? And the encapsulation boundaries, knowing what state is accessible where. So, object-oriented programming really thrives in the age of monoliths. When you have a large code base with many different components, complex interactions, it becomes necessary, at least for my sanity's sake, to be able to reason about what impact does this change have in this huge application. But if the nature of programs are such that they are getting smaller, then the need for a lot of the boundary protection might not be as necessary for all programs. And we'll get to that later as well. But we don't need as many internal boundaries, because the primary boundaries might be our internal to external boundaries. The REST request that comes in that we need to parse, we need to validate, and we need to transform into some internal domain representation. And then we use that domain representation to provide some sort of functionality, and then we create some one or many other requests where we need to take our domain model and converting it to a wire representation. But much of things that are exchanged between different processes is pure data. It's a REST request. It's JSON, it's XML, it's protobufs, it's data. But then we need to be able to model data as data, right? If we're dealing with data more primarily than we have been before, compared to the other things that we're doing, having the ability to model data in a better way becomes sort of obvious. So if we can model simple domains, which we often need to do, can be really small domains like this is a request, this is a customer number, what have you, and we need to declare a class, we need to implement equals and hash code and toString, etc. It becomes a very large exercise of work to define a small piece of data. So modeling pure data with traditional object-oriented programming is cumbersome. So it's time for us to get better about modeling pure data. And records, seal types, pattern matching, they are all designed to work together to make it easier to model and reason about and work with data as data. Do I get my REST request? How do I get that from a REST request to my data representation? And how am I able to then take that data representation, extract the information, apply the business logic, and then go the other way around, producing the result, turning it back into the JSON request or REST request. So sometimes data is just data. And more importantly, I think data should be immutable, so we can reason about what that data is. I think data should be typed so that we know what it represents. Is this a string, or is it a number? Or was it intended to be a number within a string? I think those things are important considerations. Data should be consistent. And ideally, we shouldn't make invalid states representable at all. So if you have an instance of something, then in my world, I feel much better knowing that this thing is internally consistent. By having something that isn't internally consistent, I will have to try to find out whether it is or not, and places a responsibility on me that I'm not sure I'm able to actually do, because I would have to figure out what that means. But it also means that if you have a smaller program and the primary boundaries might be the network and the process, we need to make it easy to take that step from the wire to our domain data. And vice versa. And all of these all of these things together, so if data is immutable, it's typed, it's consistent, and it's easily convertible to and from the wire or the binary representation that is externalizable, they conspire together to reduce the need for boundaries. Because if things don't change, they have been validated, they cannot exist if they aren't consistent, and it's easy for us to take that representation and getting it in and out of our process. There are fewer boundaries needed. But we still need to have natural idioms for the Java language, and this is something really important, because if you have an envisioned feature for a language, most of the effort goes into how is this most easily expressible, as natural as possible within the context of the language. So what takes time is to understand how it fits into what's already there. So what we want to try to avoid is, it's fairly common to, when you produce JSON, to use string concatenation or things like that to produce the JSON. But wouldn't it be nicer if you were able to represent your JSON as records, as a structural representation, and you could render it to JSON, or you could render it to XML, or render it to some other representation. What's also interesting is that if data is immutable, consistent, etc., and you can inspect the structure from the outside, that also means that your program tends to become more testable, because it's easier to create the structure that something needs, and it's easier to inspect the structure of something that is returned. So both producing the input and consuming the output becomes easier. So let's do a bit of an experiment. How many of you are familiar with this method signature on the Java util concurrent future interface? Cool. So this is introduced around Java 5. And what a future is, it represents some computation that is running concurrently with the creating thread, and it's doing some work to produce some value. And when you want to consume said value, you don't know whether it's already been completed or it failed or something else happened. So when you're saying, hey, give me the value, you're also saying, hey, I'm also prepared to wait for at most this time that I'm passing in. So if you look at this signature, there are a few things happening, right? We have some return type V. That is the value that we want to get out, the successful result. We have interrupted exception. That could happen if something else prevents the task that is running to complete. There could be something going wrong when we try to compute the value, so we get an execution exception with the embedded cause. Or we get a timeout exception because it didn't complete until we weren't willing to wait anymore. So if we were to take an interface like this, and we were to look at how this could be structured if we take more of a data-first approach, what could that look like? Because when you use this method, this is how you would have to deal with what could happen, right? So the result branch is in the try, and then you have the timeout exception, and interrupted exception, and execution exception all after each other, and you still need to deal with them. Otherwise, you would need to figure out whether it's okay to also rethrow them, and what is the caller going to do, etc. So usage-wise, this might not be ideal. So let's see if we can do something about that. Just a thought experiment here. So looking at the signature, what we can conclude is we have 4 different outcomes of calling this method. So it can give us a successful value, a failure with the cause, a timeout, or an interruption, or the notification of an interruption. So we have 4 distinct cases. So instead, what we could do is we define something, let's call it an async return, and it has the type parameter v, which is the type of the successful value, and it does away with the checked exceptions here, because what we're trying to model here is the data-oriented approach of this. So what does async return look like? So let's define it as an interface, async return, and we define a record called success that has some result of type v, and it implements async return v. This is rather straightforward, right? The successful case has the result, the failure case has the cause, the timeout doesn't need anything else because just us knowing that there was a timeout is information enough, and interruption as well. There's not much more information that we could want here. So just the simple notification that we got interrupted, we need to deal with it. And finally, what we can do then is we can add sealing information, saying that our async return type is sealed, it permits only these cases, and now when we use it, it looks like this instead. That looks better, right? But we still have an async result. And we can't really do much with that because, as you saw before, that doesn't have any methods on it. So we can't necessarily do anything just knowing that it's an async result, right? But what we can do is we can switch on the result, and if it's a success or a failure or a timeout or an interrupt, we can now deal with it step by step if we want to. So this is a simple case, right? Because we know that there are 4 distinct cases, and we can deal with everything in a uniform way. But what we needed to do was to upgrade Switch, bring it up to the current building code. So Switch, as a statement, has a very long history in programming. And originally, it was intended to be able to take a branch and make it faster by being able to dispatch on the integer that you were matching against the label and some code. But we've added more support over the years to support more things to switch on, right? Being able to switch on strings or enums. But you still needed to remember to write break after your thing, otherwise you would execute the next label as well. So what we did as well was to introduce the arrow syntax. So you can have the case and then an arrow instead of a colon and have a single expression, and it automatically breaks after that. And case labels, if we have pattern matching, we can make case labels be patterns. Instead of just being a 1 or a 0 or a string, they could be a pattern. And it's fairly common to want to be able to have guard expressions in there. So the when clause was added. So being able to say that if this is an integer I and its value is greater than 0, execute this branch. But that's not all. We've also upgraded the switch for sealed types. Because as I said before, if not only we, but also the compiler knows that these are the only versions or variations of this, then we can use that information. So that allows us to add more and better exhaustiveness checking using this sealing information. And also, if something is sufficiently exhaustive, it doesn't need a default case. If the compiler is happy, then the compiler is happy. And it's not only the fact that, hey, I don't need to write a default case. It saves me typing, right? That's not the thing. When you're saying that these are the only things that can happen, and you introduce a new thing that can happen, you want to know what broke. Which checks are not exhaustive anymore. So by being able to tell both your colleagues and the compiler what the valid variants are, you can now find bugs more easily. And if you did add the default case, you wouldn't know. It would just be tripped at runtime. If you're happy, or if you're lucky, you have logging. And I think it's always better to try to find these kinds of defects as early as possible. So, let me just have a sip of water. All right, so this is a pretty straightforward example, right? So we have some sealed interface color. It permits the implementations red, yellow, and green. And we switch on an instance of color, then we can see that if we're looking for red, yellow, or green, then we don't need any default case. The compiler knows that these are the valid representations. But I give you a challenge. Is this exhaustive or not? You have a sealed interface A that permits the implementations T and U, and a sealed interface B that permits V and W, and you have a record of A and B, and you see this code in a pull request. What do? Reject, right? This is really difficult, right? Because the intent is, for the person who wrote it, this is exhaustive. I've done my homework. I know that this is correct. But it takes convincing, right? First, you need to convince yourself that this is correct, and then you need to convince the people that are reviewing your pull request, right? Wouldn't it be nicer if you knew that the compiler would reject the code? It would prove it for you. It would be easier to feel calm about something like this. It's not about that, hey, this is a bit more terse and it's easier to read. It's not strictly about that. It's always nice to have more readable code, right? But this is about being able to rely on the compiler to prove things for you. All right, jumping ahead to more features. String templates, preview feature. How many of you have tried them out? That's a fair amount of people. More people should try them out, for sure. So the feature request was, please give us string interpolation. Because it's really convenient. It's also dangerous. It also has a pretty high attack surface for things to go wrong. We don't need to mention any examples. And the alternatives that we have today, they aren't that great, right? We have string concatenation using plus, concatenate strings. That's pretty unsafe as well, because we're just doing a two-string on the thing that we're concatenating. It's not super readable either. And we can use string format and do runtime interpolation and do that. But it's also error-prone, because it's not compile time, right? And string builder, which is essentially making the concatenation thing, but with more code. That's not super awesome either. And most, or many languages, have special forms of string literals for interpolation. So the interpolation is from string to string, right? And that can be convenient, right? But it's pretty limited in power if you can only do templates from strings to strings. And you still have the situation where the thing that you're included in your string template is actually a string template itself, and something goes wrong. So what we wanted to try to do is to sort of offer the convenience, but do it safely and flexibly. So we can do more things, like incorporate validation, having domain-specific transformations. So if you look at the example code here, the string template expression here combines a template processor, a literal text, so the hello thing there, and the embedded expression, which is the / curly and name and curly. And what this does is string-to-string templating. So that's why it's called str. Just string to string. But that's just the type of this template processor. But you could create something else as a result. And there's also other things, like format, that uses the more traditional string format style syntax to be able to do justification left and right, etc. But you could also imagine things like, take this string template, and this is a SQL query, and validate this query and run it against the database that this template processor was defined for. So being able to go from string template to something else is a super powerful thing. You could also imagine things like there's a raw formatter, for instance, that allows you to go from the template to the template. So there's lots of flexibility in there. But you could imagine, like, the sky's the limit here, right? You could do custom JSON object creation, for instance, by taking the string literal to be a JSON string and being able to validate that, parse that, and produce some domain representation or a tree, for instance. All kinds of things. Localization is also a really good example. And for you who were at the keynote this morning, this is very dear to me. So I have 2 small children. They are turning 10 this year, so not that small anymore, but it feels like they're always going to be small kids. But they're using the Java Playground. So, hi, Adrian and Theodore. When they write their first Java code, what do I need to teach them? There's a lot of pressure on me, right? I need to be able to teach them Java, right? And when you're presented with this as your first experience with Java, you have to jump through a lot of hoops or just defer a lot of understanding until later. And this is the complexity. And you're faced with this all at once. It's not one thing after the other at some sort of pace. It's everything at once. And we want to make that easier. We want to make software, especially Java, something that grows with you as you need more advanced features. So that means that if we can reduce initial complexity and introduce complexity as needed and required, then we have a smoother experience for people learning the language. So this goes via what is a command line parameter anyway? Like when if you just start programming, you haven't tried anything before, the first thing is what is a command line parameter? And what is an array? And how do I get that? And it starts with 0. There's loads of complexity even there. And access control is great when you have many things inside the same application, and you want to control who has access to what. But when this is all you have, it sort of has to be public, right? It's like it's an application that is not accessible. It's a weird statement, right? Static. What is static? It's something about where this thing lives and what lifetime it's connected to. It's not something that we need for our main method, right? And system out, it's interesting, right? Because system, first you need to understand and find system, but then you also need to find out, and out is sort of like a final, but it's not final because you can reassign it. And then you find print line, and then you can start to do what you wanted to do. So there's a lot of both knowing where to find something, what parts of it I need, and how do I use it. Because one thing is a dot, and then a name, and then parentheses, and one thing here is just a dot, but it's not a package, and now I need to understand how these things work. And there's lots of information and understanding that you need to have in order for you to comprehend what you're doing. But also, classes and encapsulation is about these boundaries. And we don't need them here. What is a sensible name for the hello world thing? I mean, when you create something that has a main method, how many of you name that class main? Right? You're stating something that shouldn't need to be stated, right? So we end up with something more along these lines. And I know that Brian has been talking about, we'll see what we could do else, right? How could you make it even smaller? Right here, you need to understand what void means, right? It's a deeply philosophical question. What is the void? The hard thing as a beginner as well. But this is more approachable for somebody who takes their first steps with Java. And I think being able to take this, adding more expressions, exploring what you're able to do, running it. I mean, I spend more time. I probably spend like 80% of my Java programming time in JShell and 20% in an IDE. Because I want to try to explore what the ergonomics of what I'm trying to do is, without as many helpful features as possible. What can I do when I don't know anything but the thing? And being able to explore the software that we create is an important learning exercise. So being able to grow your first application out while still understanding what each component does, I think that's a valuable proposition. So, while this may appear as just being a syntax and boilerplate things, it's not about the boilerplate. It's about the approachability and the simplicity of the programs. And being able to walk along and learn in a pace that is sustainable. It also turns out to be useful if you want to write scripts. So I typically have scripts of Java code that I paste into JShell that does stuff. And being able to reason about code from small to gradually larger is valuable. And I think the problem is also something we're trying to solve for the educators. How do you teach Java? It's always hard to sell people on the value of something before they understand what it entails to not have the thing. So if you've ever had to maintain a poorly written imperative program, you really appreciate the benefits of object-oriented programming, where you're able to say, this has access to that at this point, which is very hard in a hey, there's global variables all over the place and code up to down, right? So it's easier to appreciate features when you know what kind of pains that they address. So what we can do here is we can take simple programs and add functionality as needed. And there's a great write-up, if you're keen on reading it, on what we're trying to do with our project that we call Paving the On-Ramp, which is how do we make Java easier and more gradual as a learning experience. And there's lots of other features. I mean, if I had enough time, I could speak probably an hour more. We have statements before super that can be really helpful when you need to be able to use information before you have to call the super constructor. Reconstruction expressions, super interesting work on being able to have withers, being able to modify things without saying everything. Deconstruction patterns for classes, not only for records, and primitive type patterns, and completing the primitive type handling in Switch. Thank you.